Right, so the recording is going. What we did in the first hour was we defined the satisfiability problem, the problem where at the bottom here, the input is a formula in propositional logic. That's a formula built out of conjunctions, ands, disjunctions, ors, and negations. And the question is, does there exist an assignment of truth values to variables, 0 or 1, 0 is false, 1 is true, such that the value of the whole formula is true? If there does exist such an assignment of truth values, then the formula is said to be satisfiable, and we call the assignment of truth values that makes the formula true a satisfying assignment. And what we're going to prove now, well, we've proved that, we've observed really that the formula, that the problem, satisfiability problem SAT, is an NP problem. So it is verifiable in polynomial time by a non-deterministic Turing machine. It's solvable rather, but what we did explicitly was that we showed that it has polynomially size-bounded certificates, namely the satisfying assignment. So it's polynomially size-bounded because the size of the certificate is actually smaller than the size of the formula, than the size of the input, and that we can verify in polynomial time that a certificate is indeed a satisfying solution. So the SAT problem is indeed an NP problem. And now what we're going to do is formulate the way in which the satisfiability problem is as hard as any NP problem. And this was, well, a contribution by both Steve Cook, the Canadian computer scientist, and Levin from Russia, who did this independently. And then we're going to prove the theorem. We're going to define what it means for a problem to be as hard as any NP problem. And then we're going to prove the theorem that they proved that SAT is such a hard NP problem. The proof is a little bit involved, but on the other hand, it's not really a difficult proof. It's it's basically quite intuitive once one has the idea. So from my perspective, the real contribution the main contribution of Cook and Levin was the idea of formulating this notion of a problem being as hard as any other NP problem and giving the right definition for it in such a way that it led to such a fruitful development of the field of complexity theory following. I'm sorry, would you mind shutting the door just to cut the noise? So actually, let me just state the theorem, and I'm going to give the definition essentially in the theorem. So the theorem, this is the main result of today. So due to Cook and Levin, independently of each other. So suppose we have any NP problem. And we want to show that that NP problem is as hard. What we're going to do is show that that NP problem is only as hard as the satisfiability problem, in the sense that if we could solve the satisfiability problem efficiently, we would be able to solve L efficiently. So suppose L is let's say an NP problem. So an NP problem, that means an NP language over some alphabet sigma. What we're going to do is show that if we had a magic efficient black box for solving the satisfiability problem efficiently, then we would be able to solve L efficiently. So if we had a polynomial time algorithm for solving satisfiability efficiently, we would have a polynomial time algorithm for solving L efficiently. So how can we do that? Well, the idea is we're going to translate problems from the language over sigma to problems over the alphabet for satisfiability problems. So we're going to translate any string over sigma into a satisfiability problem in such a way that the the original string over sigma will be a member of L if and only if what we translate it to as a satisfiability problem is actually satisfiable. Okay, so we're going to have a translation. So what we're going to prove is there exists a function mapping words over the alphabet sigma into words over the alphabet for satisfiability problems. Sorry, F. So mapping words over sigma to, it's actually going to map any word over sigma to a propositional formula. Words over the satisfiability alphabet. So such that we can use this function to tell us whether or not an input word belongs to L by seeing whether f of it is satisfiable by f of the word. So one is for every input word over the alphabet for L of the problem, the NP problem we're given. Sorry, that should be a word over the alphabet. So belongs, it's a word. It holds that when we translate it to a word over the satisfiability alphabet, the formula we get is indeed satisfiable if and only if the word belongs to L. So we can use the satisfiability to test if the word belongs to L. So this is not by itself sufficient for us to know that if we can efficiently solve the satisfiability problem, then we can efficiently solve problems in L. To make sure that the whole process is efficient, we need to make sure this function from sigma star to sigma sat star, from words over sigma to words over sigma sat, we need to make sure that this function is itself efficiently computable. So once again, efficiently is going to mean polynomially time bounded. So the second requirement is that also the function f is computed by some polynomial time, so some p time bounded deterministic Turing machine. We don't know how to compute with non-deterministic Turing machines. Okay, so just to say that one says that, so if condition one here has a name, whenever this property holds, that we can use our translation between the alphabet sigma and sigma sat and the satisfiability, and then we can use the satisfiability problem to test if a word belongs to the language L. Then we're reducing the problem of belonging to L to the satisfiability problem. So there's a word for such a function, it's called a reduction, because we reduce the problem L to the satisfiability problem. So one says that f is a reduction, what's called a reduction of sat to L. And two together with 1, 2 plus 1, say that f is a polynomial time reduction, so, or a p-time reduction. So in brief, the theorem says every NP language is p-time reducible to SAT. So that's the summary of the theorem.
So we say that F reduces L SAT, right?
We say that F reduces L, it reduces the problem L that we're trying to solve to another problem.
But this theorem says one, and it also says that SAT is very ambivalent.
No, it doesn't say that. So that's the other way around. Now this theorem exactly says that. No, but this if and only if means this if and only if is what it means to say that L is reducible to SAT. The point of the if and only if is we want to be able to test whether a word belongs to L by testing whether it's satisfiable. And we need the if and only if to know that both answers, either a yes or no answer, will be
and F is not reversible. So
and the F need not be a reversible function. So there is a concept in complexity theory called about irreversible functions, very, very important concept, and that's going to be, we're going to come to that a little bit later on in the course. And indeed, F will not in general be a reversible function here.
it's not polynomial.
Well, so I mean, actually, in many cases, F can be a reversible function, yeah, but it doesn't have to be. So if F is, yeah, well, it doesn't matter really. Let's leave reversibility to later. Reversibility is a fascinating concept, but I've got enough to cover today. So anyway, so before going on, let's just make a few more definitions that for the sake of making them, because they're going to be useful later in the course. But then what I want to do is prove, the main job I want to do is to prove this theorem now. So some terminal, let's just write down some terminology. A language, or definitions rather. Definitions. So a language L prime over sigma prime is said to be NP hard if it is as hard as any NP problem. So if every NP language reduces to L prime. So the theorem above so the Cook-Levin theorem, again in brief, is just saying that SAT is NP hard. So we can reformulate. So Cook-Levin, rephrased, is saying SAT is NP hard. And the language L prime is NP complete, if it is NP hard and belongs to NP. So you can be an NP hard problem. So being NP hard just means that if you can efficiently solve that problem, then you can efficiently solve every NP problem. But a very, very, very difficult problem that's much harder than NP problems could also be NP hard. So being NP hard doesn't say the language itself is an NP language. So if we have a language that's NP hard and it's an NP language, then we say it's NP complete. So in fact, so if we've shown that SAT is NP hard, we've also shown that SAT is an NP language, so SAT is indeed NP complete. So if we can show, so once we've proved Cook-Levin, so SAT is NP complete. Okay, is that clear? So the definition of, so the point is the Cook-Levin theorem is sort of independent of SAT itself being an NP problem. We've shown that it is an NP problem, but this notion of being able to being as hard as any NP problem, this makes sense irrespective of how hard this problem is. Okay, so we have the notion of hardness. Any NP problem can be reduced to it, and if a problem is hard and itself NP, then we say it's NP complete. So what we want to do, we're going to prove the Cook-Levin theorem, the Evin theorem, and show that the satisfiability problem is NP hard. Now this is a theorem that requires quite a proof. So this is a substantial theorem. As I said, it's not really, really difficult. It's not conceptually hard, but it nonetheless requires quite a bit of work with the details. I mean, basically, what we need to do, the main thing we need to do is give this reduction function from the language, whatever alphabet we've got, from the words over that alphabet to the to propositional formulas. And then we need to check that it's actually a reduction and that it's computed by some polynomial time deterministic Turing machine. But the main work is defining the reduction. So we're going to do the proof of, and this is going to be like the work for most of the rest of the lecture. I'll try to break it into manageable chunks. So to start with, we want to show any NP language. We've got some NP language L, we want to reduce it to the satisfiability problem. So suppose L is an NP language. And that's basically all we've got to go on about L. That's it. That's the only assumption. It's an arbitrary NP language. Well, let's have the alphabet as well. So over sigma. But that does give us one very important thing. If it's an NP language, we know that it's decidable by a polynomially time-bounded non-deterministic Turing machine. So we have some non-deterministic Turing machine that has good time bounds and will decide the language. So let M so remember, a Turing machine can be written as a tape alphabet, a set of states, and transition, and it's non-deterministic, so we have a transition relation, delta. So be a p-time bounded non-deterministic Turing machine. It has to potentially be non-deterministic because L is just an NP language, not a polynomial language. That decides L. So because it's polynomial time bounded, there exists a polynomial Pn on the natural numbers such that the worst run case over all runs for an input word W, all possible runs, it's non-deterministic, so we might have many runs for the input word W, is less than equal to P of the length of W. So this doesn't quite follow from the follows, but this is not totally immediate in the definition I gave of the polynomial time bound for the non-deterministic Turing machine, because there were a few, I used the big O notation, and so it was only eventually bounded by a polynomial. But if you've just got a few cases and then you're eventually bounded by a monomial, you can add a constant to the polynomial. So here I'm not using a monomial, we can simply add a sufficiently large constant to the polynomial to make sure that this time bound. So the point is I want this time bound to be an actual upper bound for the runtime on all input lengths, not just eventually apart from the finite number of initial input lengths. So we simply add a sufficient constant to the polynomial such that this is true. Okay, so that polynomial exists. So we're going to use the Turing machine to define the polynomial time reduction. But to do this, I want to first observe a couple of points about the Turing machine's behavior. And also then it's going to be convenient to make a very mild modification to the Turing machine, the non-deterministic Turing machine M. So note that if we run M on input W, then, well, let's consider the execution of the machine. So here's the tape of the machine. Ah, right. So there was an important thing that I didn't say. So the definition of deterministic time and non-deterministic time in general uses multi-tape Turing machines. And we used that definition to then define the classes P and NP with multi-tape Turing machines. But as I mentioned in previous weeks, once we get to the classes P and NP, we could as well use single tape machines, because multi-tape machines can be polynomially time simulated by single tape machines. And you did that in the exercise class a couple of weeks ago. So we can, and it's going to be used, it'd be possible to use a multi-tape machine here, but it would make our life a bit more complicated. So it's important here that we're going to assume it's going to be helpful, rather, that M is a single tape machine. So this is the single tape. We start running it on word W. So where the word W is going to be written on the input tape. And I'm going to call the tape cells here, I'm going to number them. So here we go from tape cell 0, which is where the head starts, to tape cell here is length of W minus 1, right? Because if the first one is 0, then the last square that W occupies is length of W minus 1. So if we run M on input W, then it starts off in this starting configuration, and it's going to run, because M runs for at most P of length of W steps, because let's put the then down here. So then, because M runs for at most P of the length of W steps, the amount of tape it will see, it can only move the head, it can only move it 1 square each step. So at the most, the head can end up looking at squares up to P of the length of W. In one move, it could look at square 1 as well as square 0, where it starts from. So on the last move, the tape head could be at P of length of W itself, or the tape head might go to the left, in which case it's not going to see much of W, but never mind. It could potentially just go to the left, in which case in P of W steps, it could be in position minus P of W. So the tape head is always at a square between, so here we have the square minus 1 here, between minus P of W of the length of W and P of the length of W. Okay. Now the other thing we're going to do is the Turing machine might stop in strictly less than P of length of W times. And for our translation to the satisfiability problem, it's going to, it complicates the translation if the Turing machine stops. So we're actually going to prevent our Turing machine from terminating. I mean, the whole point of running the Turing machine for a decision problem was to get it to terminate in either the accept or reject state. But actually, we're going to prevent it from terminating by, when it gets into the accept state, it makes a step and it does nothing in that step and it stays in the accept state. And when it gets into the reject state, it makes a step and does nothing and stays in the reject state. And the point of this is that that means we can then, in simulating the machine, we can, now we've got this polynomial. What we do is we'll simulate it for exactly P of the length of W steps, and then look to see at the end of that if it's in the accept state or the reject state. So that's just going to help the translation. I'll show you why, but it's clear that we can do that. So we modify, for convenience, we modify M so that instead of halting, it makes a dummy step from any originally halting configuration. So dummy step means does nothing. So it does nothing. It's clear what that means. I mean, it stays in the same state. It leaves the head where it is, and it leaves the same symbol on the tape that it's currently looking at. Okay. So it just sort of ticks along, so to speak. And we'll call the new machine M prime. So M prime, well, it has the same set of, sorry, what order do we have things? It has the same tape alphabet because we haven't changed that. It has the same set of states because we haven't changed that. But all we've done is we've added a few more transitions to the transition relation. Okay, so these dummy steps that don't do anything. So what we're going to do is we want to translate so we're going to be given an input word W, and we want to find a formula phi of W. We want a polynomial time algorithm for finding a formula phi of W that is satisfiable if and only if W belongs to the language L. Or equivalently, is satisfiable if and only if our Turing machine M prime, when we run it for exactly P of the length of W steps, is in the state accept. Well, or rather, sorry, if there exists a run, because it's non-deterministic, such that when we cut it off after P of the length of W steps, we're in the state accept. Okay. So given a formula, given an input W, input word W. Oh. We construct, using a polynomial time algorithm to do so, a formula, a propositional formula, such that phi of W is satisfiable if and only if there exists a run of the non-deterministic Turing machine M prime on W that is in state accept after P of the length of W steps. And this is, by the way I've defined M prime, this is if and only if W belongs to the language L. Okay, because M prime was, the Turing machine M prime was, is a very small modification of the Turing machine M, which is a non-deterministic Turing machine that decides the language L. Okay, so now this is what we need to do. We have a formula that will be satisfiable if and only if there exists a run of M prime on the input W that gets into accept within the relevant time bound, okay? So to construct the formulas, I'm going to build the formula over some number of variables, because we always need to build formulas over variables. So I'm going to first tell you what the variables are. And the idea is the formula itself is going to be such that the satisfying assignments of the formula are in one-to-one correspondence with runs of the Turing machine M prime on W that end in accept. That's the idea. So we're going to use the formula itself to code up what it means to be a run of the Turing machine. And the whole beauty of this problem is that the propositional logic is exactly appropriately expressive to allow us to do this. sufficiently expressive. So phi w, the formula we're going to construct, will have the following variables. So I could write these variables as u sub something, but then I would end up writing u or v or something. I'd end up writing that a lot of times and it would be quite unreadable. So I think it's better to just, I mean, it's a variable, but I'm going to write it using some text that tells us exactly what it does. And I'm going to put brackets around to sort of say this whole thing is a variable. So there's going to be a variable. So this is just a single variable. It looks like a compound thing, but it's a single variable. State sub t equals q. And there's going to be one of these for every t. So this for every t equals 0 to pw, p of the length of w, I mean for every t in the set of numbers starting from 0. So every t equals, so for t equals 0, for t equals 1, for t equals 2, up to p of the length of w. And state q of the Turing machine M prime. And the idea is that such a variable, when it's true in the satisfying assignment, this means in this particular run, we can view t as the times. T equals 0 is the starting configuration, the time of the starting configuration. We're running it for exactly p of length of w steps. That's why we modified the Turing machine to be M prime. So t takes p of length of w steps, and this is, the time is just counting the number of steps we run it for. And then when this variable is assigned the truth value true, or the value 1, equivalently, that says on this run, the state of the Turing machine on this run at time t was q. And we're going to encode the other things, the other bits of information about the configuration as we execute the Turing machine as we go. So the configuration contains the state, it contains the machine tape. So the machine tape, we're interested in all the positions from the length from minus p of w up to p of w. So all the places the head can look. So we're going to say the symbol on the tape at time t and at position I is A. And there's going to be such a propositional variable for every, again, t from 0 to p of the length of w, for every possible head position. So the head positions now range from minus p of the length of w, if it goes left, all the way up to p of the length of w. And A can be any symbol in the tape alphabet, including blank. And lastly, we're going to record the head position at position t, at time t is so the head position will be some index, again, from minus p of the length of w to p of w. So we have a variable stating that it's true when, if and only if the head position is I. So we have one of these for every, again, t, every possible time for the length we're running the Turing machine for, and every I from minus p. So all the possible head positions. So again, that can, the furthest left we can go is minus p of the length of w, and the furthest right we can go is p of the length of w. So these are all the variables we're going to need. And look, and let's just check the number of variables. The number of variables is, so we've got rather a lot of variables. So the state ones, there's one for every time. So there's P of W, length of W plus 1 different time slots, because we also have 0. And there's one for every time and for every state. So we have P of length of W plus 1 times the number of states, variables of this form. This one here, we've got 1 for every tape position, sorry, 1 for every time, 1 for every tape position, and 1 for every symbol of the alphabet. So we're adding, again, P of the length of W plus 1 for the times, well, there are 2. So the number of tape positions from minus P of W to W, there's also 0. So that's 2P length of W. Sorry, the plus 1 should be outside the brackets here. P of W plus 1. So 2P of W plus 1 times gamma, the size of gamma. And the head positions, again, there's 1 for every time and 1 for every head position. So we're adding another of P of the length of W plus 1 times 2P of the length of W plus 1. So we can just put a plus 1 in here and put that in brackets. And this is the number of variables. So notice that this is kind of a cubic blow up in the polynomial. But the point is, this is polynomial. So the number of variables is polynomial in the size of the length of the input string. Okay, so it's 5 past now. That's another good time for a break. I'm just going to have a 10-minute break this time. Okay, so we'll start again at 1/4 past. Let me pause the recording. I need to write a little checklist of all the things to do. But so we're proving, just to remind you, we're proving the Cook-Levin theorem that SAT is NP hard. That is, any NP language can be P time reduced to the satisfiability problem. So to do that, we started off with an NP language L. Because it's NP, we have a single tape polynomial time-bounded non-deterministic Turing machine that decides it. We've modified that Turing machine very slightly. So when it gets to an accept or reject state, it idles in that state rather than actually literally halting, which means we can always, on any run the machine for exactly P of the length of W steps, where P is the polynomial that was bounding the time run of the original Turing machine. And now what we wanted to do was define for an input word W, we wanted to define a formula phi of W that satisfies that phi of W is satisfiable if and only if the word belongs to the language. But because we had this modified non-deterministic Turing machine, that's the same thing as the phi of W is satisfiable if and only if there exists a run of the non-deterministic Turing machine on the word that gets to the accept state in P of the length of W steps. And we're going to do that by encoding in the formula, well, writing the formula in such a way that the satisfying assignments of the formula are in one-to-one correspondence with the runs of the Turing machine M prime on W that after P of W steps are in the accept state. So we've got the appropriate propositional variables that are going to allow us to write this formula, and we now want to start writing the formula. So let's go onto a new sheet. So we define the formula phi of W in such a way that it's satisfying assignments are in 1-1 correspondence with runs of the modified non-deterministic Turing machine M prime on W that are in state accept after P, the length of W steps. So how can we define such a formula that whose satisfying assignments are exactly the runs? Well, essentially what we're going to do is we're going to use these variables to say that the variables at time 0 need to correctly represent the initial configuration. The variables at future times need to correctly model the stepping relation from one configuration to the next of the Turing machine. And then at the end, after P of length of W steps, we're in the accept state. That last part's easy to say. So I'm going to break phi of W into parts. Because otherwise it would be very, very long indeed, into parts. So firstly, phi init for initialization. So phi init with string W is going to say that the configuration at time 0 is the one that we expect. So we want to say that overall on all squares, so the W is written, so we want the word W to be written on the squares from index 0 up to length of W minus 1. So for every I from 0 and strictly less than W, we want to say the symbol that the head is looking at, the symbol on the tape 0 at time 0 at position I equals W sub I. So W sub I is the I minus 1th symbol of W. So we write W, we expand a word as W0. I don't know if I was starting with 0 earlier but now I am today. Okay, so W0 is the first character of W, and W of length of W minus 1 is the last character of W. Okay, so the conjunction of those. So this just means we're making a big conjunction where we've only got a binary operation, but we can just build the formula by combining lots of binary conjunctions together. And that it's useful to have this shorthand notation. We want the position of the head at time 0 to be 0. We want the state at time 0 to be the start state. And there's one other thing to say, which is on the rest of the tape that's relevant to the computation, outside these bounds from 0 up, but outside where W is written, the tape is blank. So the conjunction for over I from P of W So from minus p of the length of w all the way through to -1, we're going to have the symbol at time 0 at position I is blank, and conjunction from I from position length of w through to p of the length of w. So these two conjunctions are just saying the tape is initially blank outside the input word w. Okay, so it's just a big conjunction of stuff. Right. So am I going to fit? So maybe the next one needs a whole page. Yeah, but I'd rather have too much space than too little space. So that's so that formula phi is making sure that the initial the variables at time 0 have the right truth value. I mean, there's something else we need to say about. I'll see if anyone can think of that. You might think about that. There's still something else to say about time 0 as well, but you can think about that while I'm writing the next formula. So the next one is, I'll call phi step. So let's put colon equals, because this here we're defining the formula to be that. So phi step is going to say that the formula phi, the truth values of the variables, implements the correct step relation for the non-deterministic Turing machine. So what we want to do that, goodness me, my notes are rather messy. So what we want to say at every possible time, from which we will be making a step. So the times at which we make a step at time 0, that's the beginning. The last step is at p of length of w minus 1, because we're cut off the computation once we've made that last step, okay, when we're at time p of length of w. So from every step at which we'll make a step, from every time at which we'll make a step, we look at every possible state, every possible symbol that the head is looking at, and every possible position that we might be looking at on the tape. And the positions we might be looking at on the tape go from p of the length of w minus p of the length of w. Actually, we can't completely be there, because we've only taken p at most p of length of w minus 1 step. So the furthest away we can be from 0 is at minus p of length of w minus 1, or we could be, if we'd gone right at all the time, we could be at p of length of w plus 1. Sorry, we could be at positive p of length of w minus 1. So for every possible time, state, symbol we might be looking at, and potential position for the head on the tape, what we're going to do is put in a logical implication that if the current state on the tape is Q and the symbol is A, and the head, sorry, if the current state of the machine is Q, the symbol we're looking at is A, and the head is at position I, then we do the appropriate thing. Then we make one of the possible appropriate choices according to the transition relation of a non-deterministic Turing machine. So we're going to build an implication. Now, implication was not a formula it was not an operation in the formulas I gave, so we'll address that in just a moment. I guess most of you know how to do that. But firstly, I want a conjunction that if the state of at time t is q, and the symbol at time t at position I on the tape is A, and the head position, sorry, that should be an and the head position at time t is indeed at position I. So if all these things are true, then this implies, so this is all in this conjunction here. This implies, so just to write in a box, the implication phi implies psi, as hopefully most of you know, is defined as not phi or psi. So an implication means that if the left-hand side is true, then the right-hand side has to be true. And that's what this definition enforces. If the left-hand side is false, the implication is vacuously true. So we want the implication, if we're indeed in the state, in the configuration in which the state is Q, the symbol we're looking at, the symbol that the head is looking at is A, then what we want to ensure that the machine makes one of the possible transitions from the transition relation. So in that case, we then go to a disjunction. So this is all inside this big brackets here. So if these three things are true, then we're going to take a disjunction of a replacement symbol, sorry, a replacement state, a new state that we go to, a replacement symbol. Let's just make that Anita A, and the direction that we're going to move, such that we want to have a disjunction over all possible triples of such things. And we're the head position, we're in state Q and we're looking at A, and there'll be a finite number of transitions that we can make from that. So to triples Q prime A prime D. So what we're asking here is that QA can make a transition to Q prime A prime D. We move to state Q prime, we replace the symbol with A prime, and we make a displacement D in delta. Okay, so these are all the possible transitions in the transition relation of M prime. Sorry, this should be delta prime because it's the position M prime. And what we require then is that in the new state, the new configuration we go to, so the state at t plus 1 is Q prime, it's the new state Q prime. The symbol where the head was before, so still at I, the symbol at t plus 1 at I is now A prime. And the head at t plus 1 is, well, I plus D. So it's still I if it didn't move, if D was 0, otherwise it's I minus 1 if we move left, or I plus 1 if we move right. Okay. And just close the big round bracket. So rather a complicated formula, but hopefully it's not too unclear what it's saying. So just to remark, it's for this formula itself that I modified the Turing machine so that it doesn't get stuck. Because if the Turing machine gets stuck, we would get an empty disjunction here if it gets into a position that it can't move from. And if we have an empty disjunction, this becomes false. So we're basically saying not this. And that means that the whole formula, that if one works out what that means, it would make the whole formula unsatisfiable. So one would need to make a special case for cases in which you can't make a transition here, and that would be rather cumbersome. So it's actually easier to just put the little loops in the Turing machine so it doesn't get stuck. Right, good. So that's the step relation. So as I said, there was some information missing from the initialization data, and there's also the same information missing from the step relation. I don't know if anyone's been able to work out what that is. So what we've said about the initialization data is we've said that we've said all the variables that correspond to the, for example, the positions on the tape in the relevant from 0 up to the length of W minus 1, they all have the right characters from length of W. All the other positions on the tape need to be blank. These all need to be true. But these are just propositional variables. So for example, we might, although symbol 0, so the symbol at time 0 at position -1 on the tape is blank, we're saying that's true. We also need to say then that it's false that the symbol is any other character of this at time 0 at square -1. So here we're just saying it has to be, these variables have to be true, but we also need to say all the other variables about time 0 need to be false, because this is the complete information. And we need to say that all the way through. Here we're saying if these are true, if this represent the current configuration, then these variables are true for the next configuration. But again, we need to say in a satisfying assignment, we want basically a single run through the Turing machine. So we need to make sure that at any time, we only have one character at any position on the tape being true, exactly one character at any position on the tape being true. The head position is in exactly one place, so only one of those is true, or the other ones are false. And the state, and the state variables, only one of them is true for that time. So what I'm going to say, I'm going to call this part, I'm going to call this phi sub time sequence. So what we're making sure is that we're really having a sequence of configurations through time. And to say that, I want to say then the conjunction at all times. So from time from 0 up to the P of the length of the input tape. Then I want to say for each of the different bits of information we can give. So for the states, I want to say that the state cannot be two different states cannot be true for the same time t. So I want to have the conjunction over all possible states Q and Q prime from the set of states such that Q is different from Q prime. I want to say it's not the case that the state at time t is both Q and is also Q prime. Okay, and similar things for the head relation. So it's not true that the head is in two different positions. So now for all pairs of positions that are distinct, so the positions can range from -p of the length of W through to P of W. We want to have that they're distinct positions. So once again, it's not the case that the head at time t is in position I and it's in position I prime. Thank you very much. Oh, I have run out of space. Yikes. Well, I'm going to squeeze it in here, although it's the biggest one, but never mind. So, and another big conjunction now over, so now we want to say the symbols. So for the symbols, we want to say for every head position. So I've made a mistake here in my So for every head position, so the head position goes from P of length of W through to P, so minus P of length of W through to P of length of W. For every pair of states A and A prime, sorry, not states, for every pair of symbols in the tape alphabet, such that A is different from A prime. So a very big conjunction. Again, saying that the symbol at time t at I cannot be both A and A prime. Wow, okay, so we're nearly done. So we've said, so we've basically now said you can't be in two different states or have two different head positions or have two different symbols at the same place on the tape at the same time. You might want to say that you actually have exactly one such thing. So we can't have two, but we might want to say we have at least one. We could have a formula saying that, but we don't need to, because that's already guaranteed by, we're starting off by giving ourselves one at the start time. And because we've got the formula for the steps, the formula guarantees we always have a transition relation that we can take. So the formula guarantees that these formulas together, this one plus the previous two, guarantee now that we will have exactly one piece of information for every piece of data that we want at any time. So we really will get a sequence of configurations. And now we can finally say, oh, do I? You're right. Goodness me.
It's the most satisfying practice.
Yes, indeed. Oh, thank goodness for that. Brackets are awful, but living life without brackets would be even worse. Yeah. So if we were doing this in reverse Polish notation, Lord help us. So, yeah. Oh, goodness me, yes. So finally, the formula we want, phi, sorry, what is the formula we want? Phi sub W is simply defined to be, where is it? Oh, here, yeah, is phi is the conjunction of the initialization data, the step data, the phi time sequence. What did I call it? Time sequence. And lastly, one other thing to say. Does anyone know what's missing? I know it is surrounded by like lots and lots and lots of symbols here, but is that? Yeah, very, very good. That's the one piece of missing information. So lastly, the state we're at time P of W, of the length of W, is accept. Right. So I want to check that this if and only if is true. Phi of W is satisfiable if and only if there's a run of M prime on W that is in state except after P of W steps. Well, think about this for yourselves. Basically, we have constructed the formula so that it is true. I mean, it's self-explanatory, but of course you've got to really double check to make sure that it really works. So we have phi of W is satisfiable if and only if M prime has a run that ends, has a run on W, a run on W that ends in accept after P of W steps. So this is by construction, by the very definition of the formula phi of W. Because, as I said, the satisfying assignments are in one-to-one correspondence with runs. And moreover, the construction, well, I've given it very, very explicitly. So how do we check that's in polynomial time? Well, we just basically, I mean, essentially what we just need to do is write down that formula without the shorthand, but as a formula using the Boolean connectives. We want to see how much time it's going to take us to build and write down this formula. And essentially, writing out the formula involves all these iterated conjunctions. They're just big for loops. So here we're doing a for through up to p of length of W. We're just going through q times q, which is a finite, which is a fixed size set, so that doesn't do anything. But the biggest nested for loops we have are a for loop on the outside up to p of length of W, and two for loops on the inside. Well, this is big O of two of, well, this is also, it's twice p of length of W plus 1, but it's big O of p of length of W. So we've got two loops here. So this is basically cubic in p of length of W. So the construction of phi of W is effected. You might know there are two words effected in English. One is spelt with an A and one is spelt with an E. One almost always needs the one spelt with an A, but here we mean carried out. So effected, that's the one with an E, in polynomial time. One can check. Sorry, this should say the construction. Aha, no, this was by construction. Yeah. Moreover, I want to use the word effective, so it is effected in polytime. More specifically, big O of, in the size of the input, of length of W cubed. QED. And it's 11:15, but I think that was quite a big proof to get through. We got the break next week. I did want to cover a little bit more material, but I think this is really a good stopping point, and I've also got a medical appointment to go to, so it's good to finish now. I just want to say one thing before, so please try to sort out your student presentations. If you're having difficulties, you can try using the chat on the forum on the web page to see if people will be willing to share slots with you. If anyone's having real difficulties, get back to me and I'll see about making other arrangements. Yeah, so that's it. Have a good break next week, and see you in 2 weeks from today. So that's it for today. Sorry? Yeah, thank you. I mean, it's just to do with the operation. So. Yeah.